January 2010, buried 25 feet underground, surrounded by 2-foot-thick concrete walls in the Natanz Nuclear Facility in Iran, inspectors from the International Atomic Energy Agency, or IAEA, are completing their inspection when they notice something is out of the ordinary. These are centrifuges used to enrich uranium. Usually around 10%, or for Natanz, about 80 of the centrifuges need to be replaced each month, but over only a few months, workers had replaced 1,000 to 2,000 centrifuges with no explanation. Scientists monitoring the centrifuges see nothing out of the ordinary, but how could this be? Enter StuxNet, a computer worm of unknown origin. StuxNet used many exploits in Windows and Siemens SCADA, or Supervisory Control and Data Acquisition Systems. It used an unprecedented 4 zero-day exploits, 2 for spreading the infection, and 2 for escalation of privileges. Zero-day exploits are where even the developers of the software are unaware of the vulnerability. StuxNet was first detected in June of 2010 by VirusBlock ATA, a security firm in Belarus. They sent Microsoft a bug report about an exploit in link files, or shortcut files. Microsoft security software engineer Bruce Deng investigated this and the other Windows vulnerabilities. He analyzed the shortcut file seen here by dumping it into human parsable form. I'll let him explain the root cause.
The root cause is basically LNK files contain links to a target, right? Shell needs to know the icon to represent this shortcut. And control panel links, which is a special type of link file, has the property called dynamic icons. And in order for the shell to get the icons, what they do is they literally call load library on this. And when anybody who programs Windows, load library, when you pass it, it will execute DLL main automatically. So the end result is that you get code running like in the current user context, like automatically. The attack vectors. Okay, so once we figure out the vulnerability, but we were wondering, okay, well, usually WebDAV. What if you put it, the DLL on a UNC share on the internet or something like that? Would this work? And that was important to us because that basically means that you can exploit this. You can put your file on the internet, and you can destroy the world. So it turns out that we were able to create a repro that uses WebDAV, where the DLL is not stored on the local drive; it's stored somewhere on the internet. And when we found this out, it's like, wow, dude, it's like really bad stuff. So, yeah.
He goes on to say within minutes, developers had a fix. They now check if the applet is registered before loading dynamic icons. The second bug involves escalation of privileges on Windows Vista and 7 systems. This was noticed when rootkits were being deployed without user interaction.
On Windows Vista and higher, when you create a scheduled task, it actually stores all the information about the task in an XML file. And the XML file contains like which user the task is supposed to be executed as. So usually it's by you, right? And the task scheduler will checksum this XML file, save the checksum in a registry somewhere, and then before it executes, it hashes the file again. It checks to see if that is the same or not. Because when you create a task, you actually have readable. It's actually readable and writable. So anyways, that's how they did it. If the checksums don't match, and obviously there's some corruption, so we don't execute. But if the same, execute. But of course here, CRC32 collision is very easy. It takes like 5 seconds to generate one, and that's what the StuxNet author did. So the attack plan, here's how it worked. They create a task, which basically run DLL while it loads the driver, and then it checksums the file just before the file gets closed, and it saves the hash. Then it opens up the file again, and it keeps on padding the file until the checksum is the same, and that's boom, that's it. And then they disable the task and run the task again to bypass the caching stuff. And that's pretty much it. And what they did was they changed the current user to local system. So local system is like the highest privilege you get, I guess. So they get code running as root. Easy, right?
For the fix, they switched to a much stronger hash algorithm.
And so we changed the hash algorithm to SHA-256.
In Windows XP, escalation is done using a keyboard layout exploit. A keyboard layout for different localizations can be loaded from anywhere, including user context. Inside the load keyboard function call, an integer is assigned to the global pointer, and this pointer is not validated. So the attacker would use this to search for the last D word within user level range, allocate memory, and execute it, now in kernel mode. The fourth zero day was found when Kaspersky sent Microsoft an email about strange RPC traffic from StuxNet infected machines. An exploit in the printer spooler's guest account access was used to write files.
They wrote the moth file in system32 slash like wbam slash moth. And I'm like, what the f is special about why this directory? It turns out Windows has a thread that continues watching this particular directory for new files being dropped in there. Once a new file is being dropped in, it picks it up and it runs it.
So what is the end result of all these exploits? There is widespread infection, but not widespread problems because StuxNet was a targeted attack. It footprinted its host computers and checked for specific Siemens systems to launch its payload, otherwise it would lay dormant. It launched a man-in-the-middle attack on the Siemens systems. For 15 minutes once every 27 days, the centrifuges would spin up 400 Hz faster than normal. This would wear them out significantly faster. Then they would spin down to 2 Hz for 50 minutes, ruining the uranium enrichment process. From StuxNet, we can see that cybersecurity is now more important than ever, and cyber warfare is very real. The StuxNet source code is out on the internet for anyone to use.